Okay, good morning, everyone. We're going to get started. Thank you, everyone, for coming this morning. We're excited to have, I think this is our fourth quantum workshop as part of the Faculty Summit, so thanks for coming. We have a pretty full schedule, and we have a pretty diverse set of topics, so it should be a pretty fun day. We're going to start this morning and hear from Andras Gilyen. He's going to talk about optimizing quantum optimization algorithms, so let's welcome Andras.
Thank you, Krista. Is the mic working fine? So this is joint work with Nathan Wiebe and Srinivasan Arunachalam. I'm now an intern at Microsoft Research for the summer, and I'm working on this with Nathan, which we started in January together. So I would like to give a quick overview of my talk. First, ingredient in my talk is an improved gradient calculation algorithm, which is based on Jordan's algorithm from 2005. And another ingredient to make this fitting the machine learning applications I want to show is to calculate the gradient of success probability. And I show how it fits many machine learning applications or quantum autoencoders, quantum optimization algorithms, and so on. And on the quantum autoencoder side, there was an interesting paper end of last year. This is I want to show this application, particularly this problem. So the basic idea of the gradient calculation algorithm is fairly simple. It's based on the quantum Fourier transform. I want to show this slide on Fourier transform because it's a slightly unusual normalization of the Fourier transform. I just want to make sure that it's the same usual Fourier transform. So instead of dealing with large numbers between 0 and 2 to the n, I want to deal with basically precise real numbers. So I just rescale all my numbers to be between 0 and 1. And if I work with x and k, now I n-qubit states, which are on this grid in 0 and 1. And due to this normalization, when I do the Fourier transform, then I don't divide by n, but multiply by n. It's just the normalization goes through this way. Anyway, the Fourier transform from such a state would give me back basically the momentum of the state, the k vector. And Fourier transform is very useful in many quantum algorithms. It's easy to implement with a few gates, and it is the basis of many exponential speedups in quantum algorithms. And it's relatively insensitive to small disturbations in the phase. So it's kind of a robust method. And here is now the idea. How do you apply it to an actual gradient calculation problem? So now we assume that we have a function which is like a d-dimensional function, f, and it is given us in a phase oracle so that for value, which is now a point in a d-dimensional space, it will produce a phase which is proportional to the function value itself. So this is the input model with which we work, and I show what is the basic idea of the gradient calculation algorithm. So the algorithm starts with preparing uniform superposition over now all the points on this d-dimensional grid, which is just 0, 1 to the d. So this uniform superposition is easy to prepare. Then I apply my phase oracle, and I apply it n times so that I get an n times the function value in the phase. And now I say that suppose that this function is close to linear around 0, then I basically approximate the function value as the function value as 0 plus the gradient times the distance to 0. So it basically translates to a global phase, which is the function value at 0, and then this part, which is the linear part, the linear function approximation. And this is the same form what was an eigens, basically what was a natural, what was the image of a single momentum vector. That is the same thing that appeared here. So if I now apply a quantum Fourier transform, which is now d-dimensional, which is just meaning that I do a Fourier transform in each dimension, then I actually hopefully get back the gradient vector itself as a bit string representation, so I can actually read out this value classically. So the basic challenge here is to approximate the error and make sure that the linear approximation that I used, that's actually good enough. So for this, I assume that my function is analytic. And then one trick that I could use is just rescaling the function. I can multiply the function itself with some large number r, and also divide the variables by r. Then in the Taylor series, each term gets basically divided by a large power of r, except the constant term and the gradient itself, which remains constant. So this is a nice trick, but the problem is that since I only have oracle access to the function itself, whenever I rescale the function, basically one oracle query to the new function is r times the number of queries to the original function. So it's expensive to do this rescaling. Nevertheless, basically, this was the way like Jordan dealt with the error, and this was suboptimal. So this is where we applied some tricks from numerical analysis, and the basic idea was to use higher degree or higher order numerical differential formulas, which is basically based on an interpolation polynomial. I can do higher and higher order approximations to my function by evaluating it a few more points. So this is, for example, very nice approximation. It's easy to see that the second order term is cancelled from the Taylor series if I use this formula, and the gradient is preserved. So this, if I use this thing, which basically means that first query f for x, then do a inverse query, which is just the unitary inverse of the query function for minus x. So this is already a much better approximation to my function, which completely surpasses the second order term. And so one can push this idea further, but it's a long calculation involving some higher order calculus. But the basic theorem that we could prove along these lines is that if I have d-dimensional analytic function and all partial derivatives are at most 1, then I can find a finite difference formula of order, logarithmic order, which then satisfies that the function and the actual function, it's a typo, it should be the gradient times x. So that this function is almost the gradient times x, almost completely linear. It should be gradient f0x. And so this function is epsilon close to being linear over this d-dimensional hypercube. But so there are two subtleties here. One, that it's the symmetrized hypercube, so I need to center the 0 in the middle, then it works much better, turns out. The other thing that actually it doesn't quite work on the unit hypercube, but I need to rescale the hypercube a little bit, so it's only in a smaller fraction, but still a relatively nice fraction of the hypercube can be linearized by this trick. Yeah, so this was the analytic result that we needed to prove. And the actual query complexity after some more work, that the best theorem which we could basically prove using these results, is the following. So if I have a function which was, again, analytic, and we could slightly lift the requirements. So now the requirement is that if I calculate partial derivative, like which involves k derivation, then the absolute value of this number should be always less than some constant c to the k times square root k factorial. This is just what we could prove. And under these circumstances, the query complexity turns out to be c times square root d over epsilon. And this query result is like quadratic improvement in epsilon compared to Jordan's result. And it's also, this square root d scaling was non-rigorous and was only considering like up to second or third order terms in the Taylor series. So our proof is actually much more rigorous. And yeah, and it uses these higher dimensional tricks. And we could also prove matching lower bound. So our lower bound proof shows that actually for this class of functions satisfying this requirement on the gradient, on the partial derivatives, you actually cannot solve this problem with less queries if you have a phase oracle. And while the lower bound technique is based on the hybrid method, which was used for the original Grover lower bound, but it's not you cannot reduce it to the Grover lower bound. You need to reduce it to the proof of the Grover lower bound. And it's a bit involved, so I just wanted to quickly tell the heuristic argument why this Fourier transform needs this many queries. So now this is the argument. Suppose that f is analytic and f is upper bounded by 1 in absolute value. Its gradient is close to uniform 1, so it's kind of large, the gradient. And well, if you want the Fourier transform to actually get me back this gradient vector, then my state before the Fourier transform should be something close to this expression, where this is the important part in the phases. And so the question is, what is the typical magnitude of these phases? Because each phase I can get by a phase query. Each phase query adds at most 1 to my phase. Of course, phases wrap around, but still I need to somehow get this wrapped around large phases. So the heuristic argument is that this expression is basically the typical value is n times square root d. So gradient f is almost all the ones. So this is just the sum of the coordinates of x. And by the central limit theorem, the typical value of the absolute value of the sum of these coordinates is just square root d. And n, that was basically that was 1 over the precision. So the number of digits I can read out. So this translates to epsilon. So I need square root d over epsilon queries. This is, of course, not a proof. It just shows you why this might be the right scaling. And we have a rigorous proof as well. OK, so this was about the gradient calculation. Now, how can we apply it? So first, concentrate on the lower part of this circle, which is now a model of kind of most quantum optimization algorithms. So the idea is that you have some starting state, which is just usually the all-zero state. You have some circuit, which has some parameters. You have some gates, which you can tune. And you hope that this circuit does something that you want. There's a verifying circuit at the end, which kind of tests whether the quantum state that you prepared is a good quantum state for your purposes, and outputs 1 if it's a good quantum state. So this is kind of a benchmark, and this is the algorithm that you want to fine-tune. It could be like a like in machine learning, it could be a classification circuit, or it could be a quantum optimization algorithm, quantum approximate optimization algorithm, or quantum variational eigensolver. So it could be many things. And so these are the tuning parameters which now I added. So these parameters can be classical, and then this is just a circuit. But now I want to use our algorithm to actually somehow interact with this circuit. And in our algorithm, we needed to input these values classically. So the idea here is that the objective function which I want to maximize is the probability of measuring 1 here on the outcome. And this probability depends on the parameters of the circuit, which now I input in a quantum way. If these are rotation gates, then I can simply decompose this rotation gate as a product of rotations of exponentially increasing, like binary angles, and then basically controlled on these registers, I can do this controlled rotation. So this is how I make my circuit quantumly tunable. And just one application I wanted to show you is the quantum autoencoder thing, which the idea is that we try to compress quantum states, which are in this example 5 qubits, to only 2 qubits. And I say that the compression was successful if I can recover it with another map which takes some 0 inputs on the 3 new qubits, takes the encoded 2 qubits, and tries to restore the original state. It's similar to the classical scheme and inspired by it. And the question, the success probability of this circuit is just if I would measure now the input state, with how high probability do I actually measure the output state. So this is kind of the verification circuit, and or like actually this which undoes, which prepares the state, and this is like the tune circuit. So now I have an algorithm which works using phase oracles, and I have applications which produce me probabilities. So I need to somehow feed the two together so that I can actually use my algorithm. So I define this probability oracle, which is just on I guess, sorry, the x's are missing here, so it should have a controlled register x. So, sorry, it has the zeros, of course, because these are the ancillas that I need to use, but here I should have the x vector. So basically, on a quantum state x, it succeeds with some probability p. And so this probability can be turned into a phase, which Grover algorithm already does. So the idea of Grover algorithm, that if I can prepare a quantum state which has some probability p, then I can look at this amplitude and in particular this angle. With the Grover operator, I can do rotations of angle 2 theta. And this is almost what I want. I want something like, actually I want the probability which is sine squared theta, but I have now rotations of angle 2 theta. It's actually promising. The problem is that the spectrum of rotation is, indeed it has these 2 theta phases, but it also does a minus 2 theta phase. So I somehow need to get rid of it. I'm not, so I can imagine this as a Hamiltonian which has theta and minus theta, and I can implement the unitary e to the 2I, this Hamiltonian. But I want a Hamiltonian where this is like sine squared theta. So how can I do that? And here I use the linear combination of unitary strict. And well, it's probably too dense to digest all right now. The idea is that basically I want e to the ip, which is sine squared theta, and I just plug in this Hamiltonian because the sine square is regardless of the sine of theta, it will be always the same. And I just basically expand it in the Taylor series. I use the trick that sine is just a sum of two exponential, like two phases, and I just arrange the terms. At the end, I can end with a formula where I have the Grover operators to some powers with some coefficients. It turns out that these coefficients can be basically truncated at some logarithmically high power. So the idea is that I can actually implement this phase using a logarithmic number of Grover iterations and some linear combinations unitary trick. And well, you might would say that this is actually a nonsense thing because global phase doesn't matter. But the whole algorithm will be run controlled on some register. So this will be, in fact, a controlled phase. And the controlled phase is exactly what I want. This is what I want to put into the gradient calculation algorithm. The controlled phase is basically just the phase oracle which I was hoping for. So in fact, this probability is just, it's now not a, I wrote in this slide, it's not a controlled probability. It's just one particular probability. But this whole thing makes sense when the whole procedure is controlled on some extra registers. And yeah, just for those who are not familiar with this linear combination of unitaries, the idea is that if I have m unitaries and I have some linear operator, which actually also unitary in our case, because it's a phase oracle that we want to simulate. So suppose that I have this linear operator L, which is a sum, which I can express as the sum of these unitaries. Then using this quantum state, which I need to prepare, which encodes the coefficients, I can express this linear operator as basically first prepare on an ancilla qubits this ancilla state, then do controlled on these ancilla registers, apply the corresponding unitary, and then uncompute this register. Now this will be an unnormalized operator, and this can later be amplified. So I don't want to go into the details, but the main idea is that this quantum procedure will have a success branch, which will have this unnormalized operation, and an unsuccessful branch. And then later I can do some rejection sampling or amplitude amplification to actually make sure that I end up with a success branch. So in our case, L actually is unitary, which means that, or at least very close to unitary, like very small up to negligible error. Therefore, you actually know the success probability. And it's a well-known fact in the follow-up literature of amplitude amplification that if you know the success probability of some quantum procedure, then you can use a so-called exact amplitude amplification, which will give you the success branch with certainty. And so we can use this trick in combination with the LCU lemma, so that the previous decomposition to sum of unitaries can be actually, after amplification, give me exactly this operator which I needed. And yeah, if someone would worry about like chaining, because in amplitude amplification sometimes one needs to like undo the quantum state on which we want to apply this unitary, that's a problem, but there is a technique called oblivious amplitude amplification, which actually overcomes this difficulty. You don't need to uncompute the quantum state on which you want to act with the unitary. This is a trick with which was introduced in the Hamiltonian simulation papers recently. Yeah, and basically that's the idea. Just I want to walk through you two once more that what was the main result that we developed here. So first ingredient was an improved gradient calculation algorithm using high degree interpolation formulas or finite difference formulas, which improved Jordan's work. And then we showed how to actually convert success probability to phase, a unitary which gives me a phase back. And I showed an application to machine learning, namely the quantum autoencoders paradigm. And the new ingredient here is the quantum speedup for training optimization, which might be helpful in the future when we actually have many parameters. And well, one of the basic obstacles in machine learning is that your models have a large number of parameters, and to train it, that's the bottleneck usually. So one can imagine that if we have large quantum computers, we can actually train these models, quantum models, more efficiently. So it gives a hope that in future applications, when we have large-scale quantum computers, we can actually speed up machine learning training itself. Not only the models that Nathan talked about yesterday, but we can actually speed up the training procedure as well using quantum techniques. And yeah, that was my talk. Thank you for your attention.
Are there any questions? Oh, yeah.
Yeah, so you worked pretty hard to get that sine square theta into the exponential. But since you're using this for optimization, it seems like you could replace it by any function, monotonic function of theta. So like maybe theta square or something. So could you use that to simplify the algorithm?
Yeah, definitely. You could replace it by basically any monotonic function, which is like which doesn't care about the sign of the argument, so which is, how is it called, symmetric around 0. But the thing is that it actually gives you exactly what you want to maximize, the probability itself, which is aesthetically appealing. And also, it's not a very complicated calculation after all. So it turns out that because sine is a function which is just the sum of two exponentials, this is actually a nice and easy formula. So other functions can be harder. I didn't check all possibilities, but it is actually a natural choice in terms of formula complexity as well.
Great. Let's take another question, and maybe David, you can set up while we take it.
Oh, and just one more thing. So basically, why we use sine is because we basically want a Fourier decomposition. So a Fourier decomposition is what we can deal with because originally the Grover operator is also in sort of Fourier basis. So it gives me a phase. And I want to work in Fourier basis. That's why I want sines.
So thanks for the nice talk. I'm wondering if this improvement also exists for quantities like the Laplacian of the function or higher gradient moments.
What do you mean by exactly the Laplacian of the function?
Grad squared f.
Ah, yeah. Okay, yeah, interesting. I didn't look at the Laplacian, but for the Hessian, you can use similar tricks. Although you get like comparatively smaller speedups. So for the Hessian, you would expect a complexity classically d squared. And these methods seem to give you d to the 1.5. So it's not like the original complexity square root, but more like a square root improvement, which we've seen so far, but maybe there is some other idea which one. Yep.
Okay.
Yeah, so the classical complexity would be d squared, or for higher order things, maybe d cubed. And the quantum complexity seems not to be square root of the d power, so basically half the power, but the original classical complexity divided by square root d, nevertheless the original exponent.
Okay, thanks.
Any final questions before we go to the next talk? Okay, if not, let's thank Andras again for a great talk. Now we'll have a change of topic for the next two talks. We're going to shift to quantum error correction. And David Poulin is going to tell us some surprising new facts about quantum error correction that hopefully we haven't heard before.
All right, thank you. Thanks for inviting me. Is this mic working? Yes, okay. So yeah, I'm going to present some work that was obtained by people in my group. So Andrew Darmoine, who's currently now a postdoc in Japan, Nicolas Delfos, who's here or just about to move, and Pavitran Iver, who's still a PhD in my group. Yeah, so well, surprising. I suppose that I mean, it's surprising to me, and I'll let you be the judge after this talk. So let me explain to you like what is motivating this line of research. So let's say we want to execute a quantum algorithm which requires n logical gates, and so if you want to do simulation of a molecule like this ferrodoxin, you need something like 10 to the 12, 10 to the 15 gates. I don't know if these numbers are up to date, but that's kind of ballpark. And anyway, you'll see that everything is at best ballpark here. Each gate, so yeah, you need a lot of gates. So each gate needs to be pretty accurate. How accurate? Well, maybe the errors will add up. So you have n gate, each with accuracy delta. So maybe the errors will just add up. So the final error will be n times delta. But that assumes that the errors build up in a coherent way. Maybe they add up stochastically, in which case it might be more like square root of n delta. And we don't really know the answer to that question. And this tells us that delta, and I'll consistently be using delta for the error in the logical gate. Okay. So the logical gate need to be accurate to either 1 over square root of n or 1 of n. So given these numbers, that gives us a pretty rough ballpark, 10 to the minus 6, 10 to the minus 15, right? That's what we need to be shooting for. And in this talk, I think it's fair to say 10 to the minus 10. Okay, that's what I'll be using as an example. So we want gates that are accurate to 10 digits, let's say. Well, we know that's the fault-tolerant threshold theorem, that if the physical noise rate epsilon is below the fault-tolerant threshold, then we can use fault-tolerant error correction to build logical gates with an accuracy delta, and the overhead will cost us polylogarithmic in 1 over delta. So epsilon is the accuracy of the physical gate, and delta is the accuracy of the logical gates. Okay? So here what I want is to get a more kind of precise answer to this question. Given a physical noise rate epsilon, how much error correction, what's the overhead that I need to achieve a logical noise rate delta? That's kind of the question that will be motivating this line of research. Okay. So I will present to you results that were obtained towards answering that question. But before I present the result, let me just present the tool that I've used to obtain these results. Okay. So the summary is that if you want to simulate a fault-tolerant quantum computer with realistic noise model, well, that's a hard problem. And in fact, it's just as hard as simulating a generic interacting many-body system. Okay? So our contribution has been to use tools, numerical tools that were developed in the context of quantum many-body physics, condensed matter physics in particular, to study these fault-tolerant questions. Okay? So what tools? Well, we've been using tensor network methods. So you may have heard about things like density matrix renormalization group, DMRG, or PEPS, or the MERA. So there's tons of acronyms. And we've used each of these tools in different contexts of quantum error correction. Okay? So I don't have time to explain what these tools are, but I just want to say, they're out there and we can use them for that type of research. Okay, so to understand how these tools can help studying question and fault tolerant, we need to understand what goes into a fault tolerant simulation. Well, here are the steps that you would have to simulate. So first you need to prepare some encoded state. Typically these are stabilizer codes, so the encoded state can be represented efficiently on a quantum computer. So then you write your state as a density matrix and you apply a channel. Okay? You apply some noise to that state. Now, let me just open a parenthesis here. In many numerical studies that have been made, it was assumed that the noise was stochastic. That the noise was like, well, either this Pauli matrix occurs or this Pauli matrix occurs. And this is a great simplification. In this case, you do not apply the noise model to the state. Instead, you sample an error, and you apply that error to the state. I want to emphasize that these are very different things. Okay? So, for instance, if you sample the noise, at every stage you have a pure state. It's a random pure state, but you know what pure state you have. But if the noise is generic, like let's say amplitude amplification, you can't sample amplitude amplification. You just you take a pure state and it gives you a mixed state. There's no sampling involved. Okay? So generically, you need to just apply the map. The sampling occurs at the next step. So once you have a noisy state, the next step in error correction would be to measure the syndrome. And this is something you have to simulate on the computer. So you need to compute the probability of the various syndrome outcome. And this is just given by Born's rule. So once you have the syndrome, the next step is to decode. So decoding is the process where you are given a syndrome that gives you partial information about how the system was affected by errors. And based on this, you try to figure out what's the optimal recovery to bring the state back to its original value. Then once you've figured out what to do, you apply that correction, and then you get a post error correction state, rho prime. And you evaluate what's the difference between rho prime and rho. And that gives you, what was the logical error. And in fact, you can fully characterize. You could repeat this several times, or in fact, we do something slightly more clever. What we do is we start this encoded state is initially entangled with it in external reference. So by running this just once, we know exactly what was this channel that has been applied to the logical qubit. Okay? So this just gives you complete access to what logical transformation has been applied to the logically encoded qubit. Okay. So if you are able, before I move on, I want to emphasize that there are lots of steps in this procedure that are computationally intensive. So, okay, we said this is a stabilizer state. That's not a problem. I can do this. All right, if I apply a noise model to a stabilizer state, I get a non-stabilizer state. That requires a huge amount of RAM. And even if it's just non-Pauli noise, and that's without even mentioning correlated noise model, that would just make everything blow up. Okay, so this is just memory intensive. Now, computing these probabilities, that's computationally intensive. Okay, these are exponentially large matrices. So just computing what's the probability that if I measure this syndrome bit, I get a +1 outcome, that's computationally intensive. Decoding is computationally intensive. Then I guess, this is just multiplying by a Pauli matrix, but again, these are exponentially large matrices. So pretty much every bullet point on this list is computationally intensive. Now, I want to emphasize that this one here is crucial because all the other bullet points are about the simulation. Decoding is something you'd have to do if you had a quantum computer, right? You need to decode the information. So this is the step that has to be efficient. The other steps don't necessarily need to be efficient. It helps if they are because it helps you do the simulation, but they don't need to be. And I'll get back to this a bit later. Okay, so suppose that you're able to do all these things. What can you do? Well, someone comes up and says, here's my noise model. It's epsilon. Well, I can use a procedure and output a certain syndrome and say, here's the probability that you would have obtained that syndrome. And given this syndrome, here is the logical channel affecting your logical qubit. And typically it will depend on the syndrome that you obtain. And then you can repeat this many times and start averaging stuff over the syndrome and say, this is my average logical channel, or I could say, here's my average logical error, or here's the error of my logical average. These two things are not the same. And you can compute any statistical figure of merit that you want. Okay, so this was generic. Up to here, let me show you how this can be done for the surface code. So the surface code, the code states are PEPs. So PEPs is an acronym. It's projected entangled pair states. These are two-dimensional tensor network. So I'm saying you can write, there's an efficient representation of the state vector that does not require an exponential number of coefficients, and it's just represented by a two-dimensional lattice of tensors. If you write down a density matrix that does not change this fact, it remains a 2D tensor network. Now, I would like to apply some noise model to that state, and I would like the result to also be a 2D tensor network. So what type of noise model allow me to do this? Well, any noise model that's a 2D tensor network. Okay, if I apply a 2D tensor network noise, and I call this a PEPSO, so SO is for super operator, but that's more like a joke, but no one gets it. So it's but the point is that if I have a noise model that's a 2D tensor network and I apply it to a 2D tensor network, I just get a 2D tensor network. This is very, very general. Okay, I can do non-Pauli noise model, correlated noise model, and so on. Provided that the correlation or kind of decay exponentially, I can simulate these things. Or at least it gives me a 2D tensor network. Computing the probability of a syndrome, that's a two-dimensional tensor network contraction. The post-measurement state, I've just multiplied by a local operator, doesn't change the tensor network structure. A Pauli correction is a tensor product, so this does not change at all the tensor network structure. And computing the logical probability to do like quantum state tomography at the end is also just about contracting a 2D tensor network. So all the computationally intensive steps here boil down to one operation, contracting a two-dimensional tensor network. Now, this is hard, unfortunately. There exist efficient approximate contraction schemes, okay? But in this work, we have not used them. Instead, we did everything by brute force. So it is not efficient. It's exponential, but it's exponential in the width of the surface code, not in the area. And therefore, we were able to simulate surface code with hundreds of qubits, which would not be possible without using these tensor network techniques. Okay, so I think the biggest lattice we did is maybe, it was rectangular, so maybe 10 by 15 or something like this. But there's no way you could do this by brute force, but using tensor network, this was not a problem. So there are no numerical errors in these simulations. Okay. The other type of code, so this was surface code. We've also studied concatenated code. Now, concatenated code, this is what a concatenated code looks like. And just by looking at it, you can see, oh yeah, the tensor network behind this is a tree. And trees can be contracted efficiently. And indeed, that's the case. Now, I mean, you can think about it more intuitively, but what kind of noise model can I put down here and such that the resulting tensor network can be efficiently contracted? Well, of course, if it's uncorrelated noise, so I just have independent noise on each of these wires, but it could be a tree-like noise, right? If the noise also has a tree structure, well, then the whole thing will be a tree. It could be an MPS, so if I just put a string down here, turns out I can contract this. It could be a Mera. There's a lot of interesting noise model that I can study and still have an efficient simulation of concatenated code. Okay. So these were the tools. I know this is kind of high level, but it just gives you an idea of why we were able to carry these simulations. So now I want to present a few results that were, some of them were surprising to me, hence the title, that were obtained with these tools. Okay, so the first type of result tells us something about metrics. So remember, this was the question motivating this entire line of research. I have a physical noise rate epsilon. How much error correction do I need to achieve a logical noise rate delta? Well, what is epsilon? How do I quantify the physical error rate? Well, some people like infidelity because it has a nice statistical interpretation, and also you can measure it by experimentally. It's something that you can probe by randomized benchmarking. So that's a nice way of characterizing how noisy the physical device is. If you're a theorist, you prefer the diamond norm because the diamond norm composes well. So that's what's used in theorems. If you're lazy like me, you prefer the Hilbert-Schmidt norm because it's just like you take a matrix, you square it, and you take the trace. Nothing could be simpler. And there's a lot of other metrics. Now, and if you're not like a mathematical physicist, you might think, get on to the next slide. I don't care about norms. But it turns out that it's important because if you change norm, the noise could go from epsilon to square root of epsilon. So when we say the threshold is about 1%, is that 10 to the minus 2 or 10 to the minus 4? Okay, it makes a difference. It's important. It's important to know what metric is the right one. Okay. Now, there's been a lot of work. People were aware of this, and there's been a lot of work trying to clarify the relation between these norms in the last couple of years. So a lot of people were focusing on the diamond norm because this is the one that appears in theorems, but it's hard to measure experimentally other than doing full quantum process tomography. On the other hand, infidelity is easy to measure by randomized benchmarking, so people were thinking, are there easily accessible quantities that I can measure and that allows me to put bounds on the diamond norm, and people have done this. But so as far as I'm concerned, a useful norm is one that allows you to predict the behavior of a system when it's used to do quantum computation. If your norm does not correlate with that, well, it's not very useful. So here's how well these norms correlate. So these are results of numerical simulation for the Steen code using 2 layers of concatenation. So the horizontal axis is the physical noise rate, what I've been calling epsilon, as measured by the diamond distance. Okay, it's just one choice. Here, it's a logical failure rate, delta. And up here, this blue line is the depolarizing channel. So the reason there are like little statistical errors is because I need to sample many, many syndromes. Okay, so there are statistical fluctuation, but nonetheless, it's fairly convincing that we get a fairly accurate result. And this red line here is for a channel in which every qubit is just rotated by some small angle. And the diamond norm is some function of that angle. What are the other dots? These are random channels. So I just generate a random noise model. I measure its diamond distance. And then I run like a million simulation with that noise model. And I accumulate statistic. And this gives me a data point, like how much logical error was there given that channel. I just repeat this. I think I've done 10,000 channels here. Okay. So what do we see here? Well, let's say that epsilon is 10 to the minus 2. So I have a physical system with a noise rate, of 1%. How well will it do in a fault-tolerant scheme? Well, with Steen's code, it could have a physical noise rate, a logical noise rate that's anywhere between 10 to the minus 8 to 10 to the minus 16. Okay? Or if you want to turn it on its head and say, look, I was shooting for 10 to the minus 10, so I need to have a physical error rate that's anywhere between 10 to the minus 2 to 10 to the minus 1. Okay? So these are very extremely loose bounds that it can give you. So again, if you come up with a noise model, say this has, there's 1% noise as measured by the diamond distance, how well is it going to perform in your fault-tolerant scheme? If I answer you, I have to put error bars that span 10 orders of magnitude. Okay. And if you do more layers of concatenation, things get worse. Here, we span 14 orders of magnitude. So what's the conclusion here? The conclusion is that the question I ask at the beginning of this talk makes no sense. Okay? It is not possible to even very, very crudely predict the logical failure rate of a fault-tolerant scheme given only the noise rate of the physical channel as measured by any of the standard metrics. So I showed the previous slide was for the diamond norm, but I've tried every norm that I know of, and the conclusions were the same. So things move around, but the spread remains roughly the same. For some reason, entropy was the best, but just by a small factor, like not orders of magnitude better. So the diamond norm does not stand out in any way, so I think people should stop focusing on that norm. So the good news is that if you remember in the previous slide, or either of them, the depolarizing channel was the worst that we've seen. So this is kind of good news because most, like 90% of the simulation that have ever been done were using the depolarizing noise, and that we learned from these simulations that these were very pessimistic. Things are probably better than we think. The bad news is that this statement is norm dependent. So if I change the norm, these curves can switch. Okay? So yeah, I don't know what the take-home message here is. It's just a lot of confusion. Okay, so the next kind of question that we address using these tools are channel approximations. So as I was saying at the beginning, a lot of people assume a stochastic noise model in these fault-tolerant simulation because then you can use standard Monte Carlo and use the stabilizer formalism to have an efficient simulation. So all of this coding stuff uses Clifford circuit. If you assume that the noise model is either Pauli or Clifford, a stochastic noise model, then you can simulate the whole thing efficiently. You can do millions of qubits. Okay, but in reality, the noise is never a Pauli channel. So you need so given like a physical noise model, you need to approximate it by a Pauli channel somehow, and then do the simulation with that approximation. Okay, that's a procedure that people have been using. So one way to do this is kind of just drop the non-Pauli components in your noise model. So let me show you how this is done with an example. So suppose that your noise model is that every qubit is rotated by some small angle about the z-axis. Okay, so this is the unitary matrix that results from this. So the density matrix gets sandwiched between this unitary. So you get 4 terms here, but you're going to drop 2 of those and only keep the direct terms. You're going to drop the cross terms and say, look, I can replace this channel by a model where with probability cos square theta, nothing happens, and with probability sine square theta, I have a z error. See? So now this is a Pauli noise model, and then this is very easy to simulate. It's called the twirled Pauli approximation, and again, it's kind of a similar thing, right? You simplify the model, and then you do the simulation for the simplified model. Another Pauli approximation that has been introduced is called this honest Pauli approximation. So let me show you what the idea is. So you try to find a Pauli channel. So this is your real noise model. You try to find a Pauli channel that is as close as possible, subject to the constraint that it's further away from the identity. So it's as close as you can be without being better. Okay? So this is called an honest approximation. And now you do your numerical simulation with this Pauli approximation. In principle, you can generalize this. Ken has generalized this to Clifford noise, but you could introduce correlations. And so I think this is a very good idea, and it's very rich. So here are results that we obtained. This is for the surface code. These are threshold estimates. As I was saying, these are, you can see fairly big lattices. Okay, so the biggest one was this 9 by 17. So for some noise model, it turns out it's better to have an asymmetric lattice. And this was the case for amplitude damping. So all right, depolarizing channel is a Pauli channel. So of course, the threshold remains the same, whether you use a Pauli approximation or not. It's about 18%. Amplitude damping, the exact threshold that we found using this scheme is about 39%. Okay, that's extremely high. The Pauli twirl gave the same result. The honest Pauli was much, much more pessimistic, about 6%. And the z rotation is just weird. The exact simulation don't show a threshold. It's just weird. So I don't know what to think about this. But let's look at sub-threshold behavior. This is a bit more informative. So this is for amplitude damping. The full line is the exact result. So this is as we increase the lattice size, and for a damping rate of 9%, what's the logical error rate? So you can see it drops exponentially with the lattice size, as expected. If you replace the amplitude damping channel by its twirled approximation, you get about the same results. Okay? So this is very good. But the honest Pauli approximation is much more pessimistic, as it should, right? This honest Pauli approximation doesn't say it's a good approximation, it's just honest. So it gives you upper bound. So you might draw the conclusion that, hey, these twirled approximations are pretty good, but then you go to a different noise model, the systematic rotation channel, and now here's the exact result. Here's the twirled approximation, and here's the honest Pauli approximation. So you see again, like 6 or 7 orders of magnitude difference between these results. Okay? So what's the conclusion here? It's that it is not possible to even crudely predict the logical failure rate of a fault-tolerant scheme from known Pauli approximations. Okay? It seems like you need to simulate the real noise model if you want to know how it will behave. So the twirled approximation gets good threshold estimates in the handful of examples that we've studied. I would not take this for granted. There might be exceptions to this. So we saw that the approximations can go either way, so none of them are reliable. Okay. So I think this motivates the development of tools, these many-body tools, to simulate the exact noise model. All right, the last little bit I want to talk about is decoding. So as I said early on, there's a lot of this complexity that goes into simulating fault tolerance, but decoding is something you need to do, regardless of whether you're simulating or you actually have a quantum computer. So this thing, we should work hard to make it efficient if we can. And even for Pauli noise, decoding is in general a hard problem, but we have instances of code with efficient decoding algorithms. Sometimes these decoding algorithms are suboptimal. So generically, for non-Pauli noise, you're just making the problem even more complex. So finding a decoder that works for non-Pauli noise is very challenging. And of course, you can add correlations to this. So of course, but you can use a heuristic decoder. So you can say, all right, even though the noise is non-Pauli, when I run my decoder, I will just assume that I have a Pauli noise model and just keep my fingers crossed and hope for the best. That's something you can do. It's suboptimal, but at least you get something efficient. And same comment applies to correlated noise model. You could just, for the purpose of decoding, ignore these correlations and get something suboptimal. But our simulation method, if you represent things by tensor network, combined to efficient but approximate contraction scheme for a tensor network, provide an efficient decoder that applies to a very wide range of non-Pauli and correlated noise model. Okay, so you can have, so you get a decoder which, the tensor network is an exact decoder, and then you use an approximate contraction scheme for that decoder. So here's how well it performs. So this is for amplitude damping. This green line is if you use matching to decode an amplitude damping channel. So matching is sort of let's just pretend it's a Pauli channel, like a bit flip channel, and let's decode using the standard decoder for that. And let's see, the red line down here is the exact tensor network contraction. So this one scales exponentially. And the blue line is the efficient tensor network contraction algorithm. Okay, so essentially, by using these efficient contraction scheme, as far as decoding is concerned, we see no difference. And we have now many other examples like this. In particular, we have examples that go to much lower noise rate. And this approximate decoding is always extremely close to the exact decoder. This is another example where we've studied a correlated noise model. So this is the surface code. The way we set this up, the correlations are kind of mediated by some Ising model. And this J here just represents the coupling in the Ising model. So it's a measure of how correlated the errors are. And P is just like the number of errors, the frequency of errors. And this is a log scale. So down here you have very few errors, and here very high error. But I'm just showing this to show that this decoder can handle non-Pauli and or correlated errors. Not a problem. Okay, so just here are my general conclusions. So the question motivating this line of research was, given a physical noise rate epsilon, how much error correction do I need to achieve a logical noise rate delta? I think that first conclusion is that this question doesn't make any sense. There's not enough data in the question to provide an answer. But what we've done, we've used methods from quantum many-body physics to address this question for the surface code and concatenated code. Here are a few highlights of what we've found. For a fixed physical and noise rate epsilon, as measured by any of the standard metric, the logical failure rate can fluctuate by several orders of magnitude. The diamond norm is no better than any other norm in that regard. The logical failure rate of Pauli approximations can differ by several orders of magnitude from the true failure rate. For a given diamond norm physical error rate, incoherent noise is worst. That's what we found. I mean, we haven't gone exhaustively through all the noise model, but based on our simulation, that's what we found. And for a few examples, the twirl approximation seems to give a reasonable threshold estimate, okay? But not necessarily a sub-threshold behavior, which is what we really care about. And we've also developed an efficient decoder for non-Pauli and correlated noise on the surface code. Now, I think that these tools can become useful for experimentalists because, like, let's say an experimentalist comes up to me and says, you know, here's the noise model that I think describes my qubit in the lab. How well would it behave in fault tolerance? So this is something I can simulate. And then maybe they think, oh, you know, I have a pretty small T2, so I'll put a grad student on, you know, improving that T2. But I can use the simulation tool and say, you know what? If you improve that T2, it's not going to help you. What's really killing you is this off-diagonal matrix element in your process matrix. That's what you should be spending your grad student trying to improve, right? So I can use these tools, sort of give guideline to experimentalists. And more generally, so what we see is that just learning about the infidelity of a channel or the diamond distance is not enough data to understand how the channel will behave in a fault-tolerant scheme. And this begs the question, what do we need to know about the noise model? What are the critical parameters of a noise model which determine how well it will behave in a fault-tolerant scheme? So, you know, we have this database now with tens of thousands of channels and the corresponding behavior in a fault-tolerant scheme. And we've been trying to use machine learning techniques to try to extract features of the noise model that correlate with the logical failure rate. But you know, I'm sad to report that we haven't succeeded in doing this. But I think it remains kind of a crucial question to determine what are the critical parameters that we need to extract from experiment to understand fault tolerance. All right, with that, I thank you for your attention.
Great, thank you. Are there questions for Dave? Great.
Anyway, so I think it is really amazing that this diamond norm seems to be really useless for determining whether or not your error correcting code works. And there's also this recent result about classical error correction on this Isaac model where they do this free fermion contraction thing. And so one thing I've been thinking about a little bit is the diamond norm. The reason why people like it, it's like given the ability to given basically the ability to take anything to distinguish the channel. This is how well I can distinguish things. But these stabilizer codes don't ask those questions, right? They just ask, well, is it a polyfixable thing or not polyfixable thing?
Yeah.
And do you think there's any way to make a reasonable norm from that? Or does it also fall into this list of bad norms?
Well, I think I've reached the conclusion that this is not a one-parameter question, right? It's clearly just a high-dimensional problem, but it's about how many dimensions are there. And I don't think these necessarily will have anything to do with norms. And yeah, I have a few heuristic arguments that I could try to run by you, see if you buy that.
So when designing a code for the future, should we look at tensor decomposition techniques rather than stabilizers and base our decoding and our structures on that, on making that work well?
Well, this is definitely something that I think is important. And just as a side comment, I've designed new classical error correction based on tensor network. Yeah. So yeah.
The answer is heck yes.
Heck yes. Yeah.
Hi. So I have one more question. So when you do Monte Carlo simulations, the big problem usually is to go to low error rates. So is it still a problem for your method, or is that actually, does it solve this problem?
No, okay, now you're getting onto something. Yeah. Yeah, so you may have noticed that I report very, very low failure rate in these plots, like 10 to the minus 20 or something.
Yes.
But I haven't ran 10 to the 20 simulations. So how can I report these numbers?
Well, I mean, based on your method description, I would guess that the answer, yes, this overcomes.
No, well, it doesn't. It doesn't. But indeed, like when you do a Poulin noise model and you sample from it, you either get the right correction or the wrong correction. If you have a more generic noise model, there's no right or wrong correction. I mean, for every correction, there's some residual noise. And if you do even one run and you see that the residual noise is 10 to the minus 20, you can report 10 to the minus 20. Right, without sampling 10 to the 20 times. And this is why we've sampled, each of these data point was about 1 million sample. So this is really the typical failure rate. It's not the average, because what we've noticed is that there are serious outliers. So it could be that there's a syndrome that occurs only once every billion sample that leads to an order 1 failure. So this 10 to the minus 20 should really read 10 to the minus 9. And this remains a problem. And I think it's really important to notice that the typical error is not the average error.
Yeah, but I mean, but don't we like care in practice about actually the typical behavior? Like,
well, I think that once you
code?
know this, you can do something about it.
Okay.
Yeah. Take
But-
advantage.
Okay, thank you.
Thanks, David. I've actually got a question. Have you looked into the continuity of the logical error rates when you perturb one of the channels about one of those points?
No, but this isn't we were, okay, one thing we thought about doing is for a given channel, computing the gradient around that point. So that seems like a pretty natural thing to do that could, you know, along the lines of what I was saying. An experimentalist comes up with a channel, try to figure out what's the bottleneck in his noise model and what should he be working on. So I think this goes along this line, and I think, yeah, there's a lot to be done.
Great. And while we take these next 2 questions, maybe Ken, you can set up.
Yeah, so my question goes into a similar direction as Nathan's. Have you looked at how sensitive your decoder is to changes in the noise model? So if you assume a wrong noise model, is your decoder still performing decently, or is it completely off?
That's a good question. I haven't checked this. I don't expect it to change much. And, but what I consider big changes to the noise model. For instance, like if it's correlated and you assume it's not, then you make, you know, that leads to a substantial error. If you don't have exactly the right correlation model, which is what you're asking, I haven't tested it. I don't expect it to be pretty bad. But in some sense, it is a way of accessing the critical parameters, right? If you get this thing off a little bit and things go dramatically wrong, that thing was critical. Yeah.
So my very primitive understanding of concatenation is that every layer of concatenation sort of squares the logical error rate.
Correct.
So with your 2 levels of concatenation on the Steam code, do you see this borne out? Is there an order epsilon fourth?
Yeah, I mean, yes. So it's a polynomial with the lowest degree is quadratic. And it's not something we have tested, but I mean, this is something we've looked at a long time before, and generally, yeah, it's respected. Yeah.
So that's a very good rule of thumb about concatenation.
Yes, yes. There's, of course, the prefactor, which is important, and this is related to the weight enumerator, and this is something that we can access also numerically.
It's roughly the square of the number of fault locations, I guess.
Sorry?
It's roughly the square of the number of fault locations.
Correct.
Is that right? Yeah.
Yeah.
That can be pretty bad too.
Yeah, it can be fairly large. Yeah.
Great. Let's thank David again for a wonderful talk.
Thank you.